Hello students, good morning. So in the previous class we discussed Gauss Law and some simple problems based on the Gauss Law we are discussing. So some more examples are there in that. So we will continue those examples, some simple problems based on the Gauss Law. And later we will go to the next applications of this Gauss Law. I think in the last class by mistake some problem was not completely recorded. And so now I will continue that problem. So that is, so actually we discussed a problem like when the charge is placed at the center, exactly at the center of a hemispherical sphere, we discussed that already. So the total flux passing through that will be equal to, if a charge q is placed here, then q by 2 epsilon naught we can write, right? This is the total flux, or I can say net flux. And in the same case, I can also write this flux passing through this curved surface will be equal to, this will be q by 2 epsilon naught only will get, because the flux passing through this plane surface will be 0, because their electric field direction will be like this and area vector will be like this, and so they are perpendicular to each other, and so that flux will be 0. Only that whatever the total flux that is there, that will be passing through the hemispherical surface only. This example we already discussed in the last class, right? And so now here I am explaining about the case. This is a hemispherical surface. Now a charge q is just placed outside, say at a distance of, say we representing with the delta. And here actually this delta is very small. Very small in the sense you can consider that this delta tends to 0. It's almost 0. That means simply here, even though I am representing by this distance, actually it is not by the distance. So to represent, to understand that it is outside, that it is not at the center, I am representing this charge here. So it is very close to the center, but it is not at the center. It is just outside that hemisphere, we can say, just outside the hemisphere. So that is what I mean to say here. Delta is 0 means. Now in this case, we need to answer about what is the total flux passing through that, and what is the total flux passing through the hemisphere, and what is the flux passing through the plane surface. We need to answer that. That means we need to find total flux, and the second one is flux through curved surface, flux through the curved surface, and the third one we need to find is flux through the plane surface. So we need to answer about these three questions here. That means again I am saying that the difference between that previous problem and this problem I am going to explain here. In this previous problem, we are considering that the charge is placed exactly at the center, right? And now here it is placed just away from the center but not at the center. So that I am representing it by a distance. Delta is nothing but distance. It is placed at a distance of delta from the center, and the delta is very small, tending to 0. So now in this case we need to answer the total flux, flux through the curved surface, and flux through the plane surface. So now first I am explaining the flux through the total flux. And so now I am writing this total flux here. So in this case, can you say what is the charge enclosed? Charge enclosed by our surface is, now it's the surface itself, let us take it as a Gaussian surface. Now what is the charge enclosed by the Gaussian surface? 0, right? Because charge is outside the sphere, outside this hemisphere, and so that no charge is present inside that, and so charge enclosed is 0. And so from that we can write this, the net flux or the total flux we can write as 1 by epsilon naught times 0. So that means total flux is 0. And so from the previous examples we can write, as the total flux is 0, this is our answer for this first question here. And so now as the total flux is 0, this total flux we can write as flux through the curved surface plus flux through the plane surface. This value is equal to 0, right? And so let it be equation 1. And now let us answer about the flux through the curved surface. And so in the previous example, that means in this example, when it is exactly placed at the center, we calculated that flux through the curved surface as q by 2 epsilon naught. And so now when the charge is placed exactly here, that means just away from the center, then also I can write that the flux passing through the curved surface is almost remains same, almost q by 2 epsilon naught only, because the distance what we are taking here is very small, whether it is placing here or very close to that charge, very close to the center, almost the flux electric field at any point on this hemisphere almost remains same at any point on the curved surface of that hemisphere, right? And so flux through this curved surface can be taken as again q by 2 epsilon naught. That is because this distance is very small. Got it? If this distance is large, for example here if this distance is r by 2, then you can't take that approximation there. The distance is very small, that is already given in the data itself. The charge is placed at a very small distance from the center. And so that we can approximately take it as flux to the curved surface is q by 2 epsilon naught we can consider here. Therefore I can write, so flux through the curved surface is equal to q by 2 epsilon naught. Got it? Why we are taking q by 2 epsilon naught? From this example we are taking that almost it remains same. And so now here, let us substitute this value in this case here, in this equation. That means we need to find now flux through the plane surface from equation 1. So we can write that flux through the plane surface is equal to negative of flux through the curved surface we can write. Therefore flux through the plane surface will be equal to minus q by 2 epsilon naught we can write. So this will be the flux through the plane surface, and this is the flux through the plane curved surface, and this is the flux through the net flux through the total hemisphere. So now that is actually the difference is this one here. Here the flux through the plane surface in this example is 0. Because here I already explained here, because the electric field at any point electric field lines will be tangential to that surface, area vector will be perpendicular to that, and so that flux to the plane surface will be 0. But here flux to the plane surface is not 0. It is exactly equal to the flux to the curved surface, but it is opposite sign, because flux to the plane surface will enter the electric flux through the plane surface and it will come out of this curved surface. Here actually by observing the diagram itself we can conclude that. That means whatever the flux entering here, if the lines of these electric field lines are entering like this, for example, so whatever the lines, now we can observe that these lines are not parallel to the plane surface. So that means now they are making certain angle. Now whatever the lines entering here, those lines only will come out of this curved surface. Whatever the lines entering from this base here, suppose our base is a circular plane like this. So then whatever the lines entering through this curved surface, that means plane surface, those lines only will come out of this curved surface here. So that's why their magnitudes are equal. The only difference is through the plane surface, if this charge is positive charge, through the plane surface those lines will enter, and so that flux is negative, and through the curved surface those lines will come out here. So that is only the difference there. So that is the flux through the plane surface and flux through the curved surface and net flux. So here you can observe that net flux is 0 here because no charge is enclosed here. Next let us see such a simple examples based on this flux calculation. Next I will take this cube example. So let us take this a cube of side L. Now a charge is placed at the center. A point charge Q is placed at the center. So in this cube only different cases will be there. So the first case I am taking that when charge is at center of the cube. We are taking all our point charges only. Center of the cube. So we need to write the total flux. So can I say total flux through the cube? Just again basing on our Gauss law. Our Gauss law is nothing but whatever the charge enclosed here, then total flux will be equal to 1 by epsilon naught times a charge enclosed. And so now here we can take it as charge enclosed is nothing but Q. So I can write it as Q by epsilon naught. That is the total flux here. Now here only sometimes I will ask what is the flux passing through the each phase. So flux through each face of the cube. So flux through the each face we can write as. Now simply you can observe that we are placing the charge at the center of the cube here. When the charge is placed at the center of the cube, the whatever the flux it is coming from this charge here, that flux will be equally distributed among all the 6 faces. That means here 6 faces are there. So then you can write this total flux through the each face will be divided equally among all faces. That means it is divided 1/6 of this total flux here. The total that means flux passing through each face is nothing but 1/6 of net flux we can write. And so which is flux through the each face will be equal to Q by 6 epsilon naught we can write. So that will be the flux through the each face, right? So flux through the each face is nothing but Q by 6 epsilon naught. And so now here that is the flux through the each phase. And next here in this, not only in this example there are 6 phases, so that we are writing that whenever such a symmetrical diagram is there, regular diagram is there, and we are placing the charge at the center. If suppose that the diagram or that object is having n sides, then we can write this as flux through the each phase will be, we can write it as in general 1 by n times the net flux we can write. This is a general formula. For example, if the body is a regular object and that means it is having some identical n identical sides, and now the charge is placed at the center, geometrical center of this object, then we can write that flux passing to the each phase as 1 by n times the net. So there you should observe that when this formula is applicable when only the body is symmetrical and we are placing the charge at the center, right? And next in the same example, suppose if charge is placed at the any one face, so when point charge is placed at face center of the cube, when point charge is placed at face center, like suppose if you are taking this is one of the face here, we are placing it one face. Suppose I am placing here a point charge Q is placed on this center of this face. And so now similar to our previous hemisphere problem, when the object is placed at the center of the hemisphere, then we consider that charge belongs to that hemisphere is only Q by 2, right? So here also the same concept. Whenever the point charge is placed on the boundary of an object, boundary of a given surface, then we need to take that charge belongs to that surface will be only half of the charge we need to take. Actually we need to consider a symmetrical surface there, a symmetrical object, so that it forms a complete object there. Now for example, simply what I am saying is, if you are taking this object is placed at the center of this face here, center of, let us consider this is one side of such a cube. So if you are placing at the center, that charge will belong to, if you are combining these two, then it becomes an internal charge. So for this whole two objects, two identical cubes we need to consider here. When you are taking the two identical cubes, that charge will become an internal, because this point charge will belongs to here, that means we are placing here half of charge will belongs to this cube and other half will belongs to this cube here if you are taking them as two cubes. And so that means we need to assume an additional cube there. If you are taking another cube, identical cube here, then the charge q will become the inside. And so total flux passing through both the cubes will be equal to q by epsilon naught we can write. And from this given cube, it will be q by 2 epsilon naught we need to write. And so then total net flux through the cube we can write as q by 2 epsilon naught. So that means that is the flux passing through this given cube, which is we already written in case of hemisphere. Whenever an object is, that is not only for the cube or for hemisphere. So whenever the object point charge is placed on the boundary of a surface, then the charge belongs to that will be equal to, that means charge belongs to that part will be equal to q by 2 we can write. Now in this only, instead of placing at the face center, suppose if it is placed at the corner. So now let us see that one. If the charge is placed at the corner, suppose in this I am taking this charge is placed at this corner here. So I am giving some names also here. Let us take this as A, B, C, D, E, F, G, H, right? And so now in this we need to write the flux passing through that total flux. So first to mention this case here. When point charge is placed at any one corner of the cube. So when point charge is placed at any one corner, so suppose here in this example we are taking that it is placed at the cube, means at the corner B. So we need to write now total flux passing through that cube. So total flux through the cube. So can you say how much it is? So I think in chemistry, in crystal structures, you got such a cases there. In crystal structure, like face centered, body centered, like there we will discuss actually such a type of here. That means now here we need to identify how much fraction of that charge belongs to this cube. So that will become charge enclosure. So then based on that we can write total flux associated with that cube or passing through that cube we can write here. So when the charge is placed at the corner, how much of that cube will belong to this? That means simply you need to consider like if you are placing like that. So if you are cubes we need to take, how many identical cubes we need to take so that the charge becomes an internal, inside, completely inside. Like here I said, in order to get the charge becomes completely inside, we need to assume another identical cube so that the charge will be shared between, the total flux will be shared between those two cubes here. And so similarly here, in order to get the charge completely inside, we need to take such 8 identical cubes. Like suppose simply I am taking this example here. Suppose this is, let us say charge is placed at this corner for example. This I am assuming it as a cube. It's not actually a cube, I am assuming it as a cube. So now this is topmost corner for example. It is lying at the topmost corner. Now see this. So this, like this we can place another additional cube. So this becomes 2 cubes. And so here I can place another cube here. This corner I am taking the charge. Listen again, this corner I am taking the charge. So this is, that means 2 cubes now. This is the third one. That means these cubes are sharing that corner. I am representing that. All these cubes what I am placing here, those cubes are sharing that corner. And so I can place like this. This is 1, 2, 3 like this. In addition to this, we are placing 3. Like this, on the top we can place here. Again 4. Like this we can place. Now this corner will be shared here. And so above this we can place here. And similarly like this. Above 4 also we can place here. So that means here 1, here 1, and here 1, and here 1. We can place such a 8 8 cubes. The charge will be shared by total 8 cubes. And so now total charge is now 1 by epsilon naught times. Now charge belongs to this cube will be q by 8 we can write. And so that it will be q by 8 epsilon naught. So imagine that if you are placing such a 8 cubes in corner, that means 8 cubes in contact. 8 such a identical cubes are placed in contact. 4 on the one plane and above that another 4. That means suppose on the floor, if you are placing the 4 cubes in contact with each other, and exactly above them again place another 4. So total 8 cubes will be there. Now that midpoint of the total 8 cubes is nothing but our one of the corner here. So that corner is shared totally 8 cubes, between 8 cubes, so that it is q by 8. Now this is a flux passing through this, net flux passing through the total 8 cubes. Now actually in this problem, sometimes they will also ask about what is the flux passing through the phases, different phases. Like suppose in that, if I ask what is the flux passing through that phase A, B, C, D. So let us take that phase. I am asking that flux passing through this A, B, C, D. So now simply you can identify here. Simply we know that flux here electric field line. Suppose if I draw the electric field line on this plane at any point here or at any point on this plane A, B, C, D, if I represent the direction of electric field. So the direction of electric field is, it will be parallel to that plane you will get. Suppose if I consider here, the direction of electric field will be like this. If I consider a point here, the direction of electric field will be like this on that plane. That means if you are taking the charge is present at this corner, now the electric field at any point will be tangential. Here if you want to find, it will be tangential like this, it will be tangential like this, it will be tangential like this. So if the charge is at this corner, then electric field at any point on this plane will be parallel to that plane only will get. And so that electric field will be parallel to that plane. And so now if I represent area vector will be perpendicular to that plane you will get. And so that flux passing through that phase will be then, that means E into A into cos 90. So that will be 0. Flux passing through that plane surface will be 0. Similarly, let us identify such a plane surface here. This plane A, B, G, H. On this plane also, if I want to represent electric field, you can say like this. That means simply you can identify that as, at that corner, 3 faces of the cube are meeting with each other. They are intersecting with each other. 3 corners of the, that means 3 faces. 3 face, that corner is common for the 3 faces. Now flux passing through those 3 places will be 0 only will get. Because one of such a phase is what we discussed now, A, B, C, D. This is one phase. Another phase is A, B, G, H. That is another plane or another phase. That means on that phase also electric field will be parallel to that place only you will get, because the charge is lying on that plane only you can consider. Right? And so now similarly the back surface B, C, F, G. This is another plane here. So on this plane also you can consider that electric field will be, suppose if you are taking a point on that back side plane, the electric field will be lying in that plane only will get. And so that the total flux passing through those 3 phases will be 0. Is it clear why it is 0? For example, if you are taking this board as one of such a plane, if suppose the charge is present here, if the charge is present for example here, if I ask the direction of electric field will be like this. So at any point on this plane will be parallel to the plane only will get, if the charge is lying on the plane itself. And so area vector will be perpendicular to that. If I ask the flux passing through this plane surface will be 0. So that because of that reason flux passing through these phases A, B, C, D, A, B, G, H and back side B, C, F, G. That means the phases at which that corner is common for all those 3 phases. That means A, B, C, D is one phase and another phase is A, B, G, H and another phase is B, C, F, G. For all those 3 phases flux is 0. The reason is E bar is perpendicular to A bar. That is the reason why that flux is 0 means. And so now the flux passing through the remaining phases. So if I ask what is the flux passing through, for example, AHED, the front face of this cube. The front face means this one. Similarly, this bottom CDEF and GH, that means EFGH, these faces, remaining three faces. So you can observe that remaining three faces will be symmetrical about that, charge. And so whatever the flux emitted, that means whatever the flux passing through that cube, that will be shared between these three faces equally because they are symmetrical. Suppose in this closed room, if you consider, charge is at one corner. Now, if suppose the charge is at this corner of this room, if you consider, then we are saying flux passing through this wall is 0, flux passing through that wall is 0, and flux passing through the top surface is also 0. In a room, for example, if you are taking at the topmost corner of any one of the corner, if you consider, then flux passing through, for example, in this room, I am taking this wall and that wall and the top. Those three walls will be flux passing through, those three walls will be 0. And the remaining flux, whatever the flux coming out of this cube, that flux will be shared between this wall and that wall and the floor. And so then that is nothing but what we are writing here. And so then this is another phase is, so bottom floor we can write, that is CDEF, and the next one is flux passing through EFGH. Yeah, this will be equal to 1 by 3 times the total flux we can write. Because whatever the total flux is there, that flux will be shared between these phases. So this is, we can write this as 1 by 3 into Q by 8 epsilon naught. So which will give us Q by 24 epsilon naught. So that will be the flux passing through all these three phases there. So like that we need to calculate the flux passing through each phase. So net flux is Q by 8 epsilon naught. Flux passing through those three corners will be, those three phases will be 0. And the flux passing through the remaining three phases will be 1/3 of the net flux we can write. So Q by 24 epsilon naught we can write. So that is the flux passing through different phases there. And next year in this cube example only we can consider another thing like this. Suppose here a line of charge lambda is given for us, linear charge density lambda. Suppose it is very long, the line of charge is very long. This is a side of say A, the cube side is A. Now we need to place that line of charge inside this cube, that means passing through the cube, so that maximum flux passing through that cube. So that is we need to answer here. That means if you are arranging this line of charge passing through this cube, then what is the maximum flux that can flow through the cube? So the maximum flux we need to answer. That means to identify what is the maximum flux, so first we need to decide how to place this line of charge. So in which way we need to place the line of charge so that maximum flux passing through that imaginary cube there. So right, how to place? For example, if I am placing directly normal to these faces here, suppose along this line if I am placing here from this face to opposite face, then the maximum length that can be inside this is A. And if I am placing, that means to get the maximum, I think all of you can understand that easily. We should place this line of charge along body diagonal. So if you are placing along the body diagonal, that means starting from this corner to passing through this corner here. If I am placing this line of charge like this, if line of charge is placed like this, then maximum charge will be enclosed here, because maximum length of this wire will be there inside this, or line of charge will be there inside this. And so that length you can write it as root 3a, So I can write this as Q maximum is equal to root 3a into lambda. That means maximum length will be root 3a, body diagonal length, and into lambda. That gives us maximum charge. And so that the maximum flux will be equal to, this maximum flux passing through the cube will be equal to Q maximum by epsilon naught. So which is nothing but this phi max is equal to root 3 lambda a by epsilon naught we can write. So this will be the maximum flux here. So just to mention that a line of charge having linear charge density lambda is to be placed inside a cube such that maximum flux pass through the cube. You may note them as some points or some examples such that maximum flux passing through the cube. And there we mentioned that to get the maximum flux it should be placed along the body diagonal. To get the maximum flux it should be placed along the body diagonal. Therefore you may write this maximum charge inside. This is a maximum charge inside the cube. So similar to this, there is another problem is there. Like suppose we are placing here totally 12 edges are there. 12 infinitely line of charges are there here. They are placed along the edges of this cube. Got it? Along the 12 edges, 12 infinitely line of charges are placed. All of them are having this linear charge density lambda. So write that as a problem. So 12 identical line of charges, each of linear density lambda are placed along the edges of a cube. Then find what is the net flux passing through the cube. So for this we need to write net charge enclosed by the cube. Can you say how much charge is enclosed by the cube? This is a cube of side L. This side of this cube is I am taking for example L. And note that one also. The side of the cube is L. So then can you say how much charge? Means actually we are taking a cube. Along each side a line of charge is there. A line of charge is passing through along the each side of that cube, right? And so then They are asking that and all they are having that same linear charge density lambda. Now they are asking that what is the charge passing, what is the flux passing through that. So now for that we need to calculate that what is the charge enclosed by that cube. So then can you say what is the charge enclosed by the cube? So that means if you are taking for example a line of charge of length L, then we know lambda into L is the charge present on that line. And so now for example if you are taking this line here, this line for example I am taking here. Now this is our cube. I am docking this one. So I will mention this extended part as some dotted line here so that there is no any confusion for you. So that means this is our cube here. So that is our cube here. Right? And so now in that, for example, if I am taking this side, or for example, let us take this side, the charge so the charge present on that part will be equal to lambda into L. And so now that charge is not only belongs to this cube, right? So that charge is shared by total 4 cubes, right? Each edge if you are taking, another cube is placed in contact with it. Now this side for example if I consider here, this side is common for total 4 cube. Exactly beside this we can place 1 cube and exactly back side of, then you will get front 2 cubes you will get. Exactly back side you can place another 2 cubes. So total 4 cubes will, this means this side will be common for total 4 cubes, right? And so that I can write this charge belongs to this will be lambda L by 4 into such a how many sides are there? 12 sides, right? Got it? Each side, that means if you are taking this edge here, this edge is common for 4 cubes. So that means whatever the charge lambda by 4 is there for on this edge, that charge belongs to that 4 cubes. So now charge belongs to our cube, one part will be equal to lambda by 4. So lambda by 4 into such a 12 parts are there. That means for example if you are taking 1, 2, 3, 4, that is vertical 4, and here 4 will be there horizontal, and here horizontal 4 will be there. So total 12. And so this charge enclosed will be equal to, I can write this as 3 lambda L. And therefore from this we can write the net flux. 1 by epsilon naught times the charge enclosed or charge inside this Gaussian surface. Therefore I can write this as 3 lambda L by epsilon naught we can write. Got it? So just you need to identify here how much charge belongs to that cube. And next similar to this, and based on the cube only we can write, just we will ask sometimes a graph here. Let us see this problem. Suppose I am taking this a cube of side A. Now here this is a line of charge I am taking here. This is a line of charge having this linear charge density lambda, and so now it is moving with the velocity v, right? Now here the question is, this line of charge is this imaginary cube we are taking here. This is an imaginary cube of side A we are taking, and this is a line of charge having this length L. Now this line of charge is moving with the constant velocity. That means it is ready to start at t is equal to 0. It is starting. It starts entering this cube here. Then we need to draw the variation of the flux with the time. Variation of the flux passing through the time. So just to mention that question, write it as that question there. Through an imaginary cube of side A, through an imaginary cube of side a line of charge of length L, having linear charge density lambda, is starts entering at t is equal to 0, starts entering the cube at t is equal to 0 and moves with the constant speed v. Then draw the variation of flux through the cube. With the time. When L is, write the three conditions here. When L is less than A, L is equal to A, and L is greater than A. So under those three conditions, we need to draw the variation of the graph. So let us take this first one here. Set t is equal to 0, suppose it starts entering here, right? So then after some time if I consider here, now already some length will enter here. So this length we can write as how much length it is there inside me. Suppose I am taking it as some x length already entered this. At time t is equal to 0 I am starting now. So that means we can write it as at any time t. So we can write it as length of wire inside cube is equal to x is equal to, I can write it as v into t because it is moving with the constant speed. So therefore this is the charge inside, q in means. I will write here therefore charge inside the cube. So q in is equal to, we can write it as lambda into x. And so therefore it is q in is equal to lambda into v into t. And now from this here we need to answer this maximum possible length also. That means the maximum possible flux also we can write. And from this let us write flux at any instant also. So that means flux we can write as this is a net flux through the cube 1 by epsilon naught times q in. Therefore this net flux will be equal to lambda into v into t by epsilon naught, right? Let's suppose this is equation 1. So that is a flux at any instant of time. That's a general expression irrespective of these conditions, right? Whether it is L may be greater than A, less than A or equal to A, irrespective of that we can write at any instant, we can write in that expression there at any instant of time. Now we need to consider these expressions here. Now if suppose if I consider like if L is greater than A, so then what will happen? If L is less than A, or that is our first condition. So the first given condition is L is less than A. So when L is less than A, what will happen is at some instant of time, the total rod will completely enter into this. Means I am representing here, just I am taking this cube as a face, one square here. So when it is completely entering here, right? Now this L length is there inside only. So L length is there inside only. So that means now the charge present in this cube in this case will be q into, that means lambda into this value is nothing but L you can write, right? and now that charge will remains constant until this instant here. So after certain time, then you will get this instant here. So from this instant to this instant, the charge enclosed will be equal to maximum, and that maximum charge will be equal to lambda L, right? So for that period, the charge inside the cube will remains constant when it is leaving this space, and till it touches the opposite phase during the time interval. During the time interval, charge inside the cube will remain same when L is less than A, and that will be equal to lambda L. And so that for that period of time, the flux passing through the cube will remain constant. So I can represent this variation as this flux versus time is equal to, initially it is directly proportional to T you will get, and so the flux goes on increasing here, right, and it reaches at a maximum value, and it remains constant for certain interval of time, then it decreases. Now this maximum value is nothing but you will get lambda L by epsilon naught you will get. So that is our maximum value here. This is our maximum flux. So I am writing here phi maximum, so which is lambda L by epsilon naught. Got it? So that means it is initially increasing, it will remain constant for certain time interval, which is lambda L by epsilon naught. When it starts coming out here, then automatically flux goes on decreasing, and so that flux goes on decreasing, and when it completely comes out of this cube, then flux becomes 0. So that is first case here. And so now similarly you can write in the remaining two cases. What will be the difference you can identify here? By identifying the difference you can write that value. So now if I consider the second case, so the only difference is, so when the rod is completely entering into that cube, complete length is there inside, it will be only takes place at a particular instant of time only. So I will draw this. So I will rub this diagram now. So simply let us take such a diagram, then you can understand it easily. So now I am taking the second case now, when L is equal to A. So initially it will remain same only. Initially this expression will be valid only. Now at the instant, maximum value I am discussing here. So when this rod is completely inside like this, so this total length will be there inside, right? So which is exactly equal to the side of this cube here, right? And so now this will take place only at a particular instant of time only. So in this case, the Q maximum will be equal to, maximum charge enclosure will be equal to lambda L you can write, or which is nothing but lambda A you can write, because lambda is L is equal to A, right? And here the difference is, this amount of maximum charge will remain only at a particular instant of time only. Later, that means just before this instant, the length of the rod will be like this. Just before this instant I am taking here. And just after this instant, the length of the rod will be like this. Some amount of length which will comes out here. Right? So at a particular instant of time only, this situation will be there. And so that you will get this maximum flux only at a particular instant. This part of the graph won't be there. It increases and then immediately starts decreasing. So that will be our situations there. And so then I can draw this graph as first increasing and then decreasing. And so now here this maximum flux will be equal to, this phi maximum is equal to lambda A by epsilon naught we can write, because Q maximum is lambda A we can write. So that is the case in this case here, where it is completely inside this. So then you will get the maximum, right? And so next let us take the third case also. So initially why we are drawing the straight line passing through horizon means this graph. This phi is directly proportional to T here. So directly proportional means you will get a straight line passing through the horizon while entering, that is. And so now let us take this third case here. So this third case is nothing but, if L is greater than this A, when L value is greater than A. So when L value is greater than A, then I can represent the situation like this. So at the instant of time when when the rod touches this end, I am writing here. So L value is greater than A I am taking. So this is the instant. So rod is moving like this. At a particular instant of time, this rod will touches this opposite face. So then the charge enclosed will be equal to, this Q maximum will be equal to lambda into L, right? Now again this amount of charge will remains inside this for particular time, that means remains constant for particular time. Why it remains constant means the charge will remains constant until this end of this wire reaches this face here. That means until this part will takes place, until this rod will come like this. So this Q maximum is lambda A, here A is the side. Got it? So this charge, whatever the charge here, that remains same. So that lambda A and this also lambda A. So for this entire period of time, from this instant to this instant, is it clear? Initially this front end of the rod is touching this face here. From that instant to until the back end of the rod is touching this face here. Between those two instants, the charge inside this cube will be lambda into A only you will get, because this total length is occupied by some part of the rod here. And so that in this case again the flux reaches to certain maximum value and then it remains constant for certain interval of time. So similar to that graph you will get, but lambda maximum value will be different. Lambda maximum will be phi maximum will be lambda A by epsilon naught we need to write. Here and here maximum flux are same, but the shape will be different. These two shapes are similar, but the maximum flux values will be different there. So that is the different possibilities there in such a case. So that means from all this you can simply understand that we need to identify whenever you are writing the flux passing through given surface or what is the flux associated with the given surface. Just we need to identify that how much charge is enclosed. So we need to identify just how much charge is enclosed inside this given surface. So from that you can easily write what is the flux passing through that. I will give you another example for this. This is a line of charge, for example. It is placed near a sphere. This is spherical surface, or let it be imaginary spherical surface of radius r, which is placed at a distance of d from this. So we need to answer the flux passing through this imaginary spherical surface when d is greater than or and when d is less than or. So like that we need to answer that, right? So write that as the next question. A wire of linear charge density lambda, is placed near an imaginary spherical surface of radius r at a distance d from the center. At a distance d from the center of the sphere. Find flux passing through the spherical surface when d is greater than or and when d is less than r. So the first case I am taking here when d is greater than. So when d is greater than or, the given diagram is itself is clear. So then what is the charge enclosed by the sphere? So no charge is enclosed here because the totally line, we can write this flux passing through that surface is 0. So right, got it? Flux passing through that surface is 0 because total charge is outside only, so no flux is passing through that. And so now let us take this second case. When D is less than R, D is less than R means our situation will be like this. So then here this is our D now, and this distance will be R. And so now this is, suppose I am taking this as X from here to here. And so then this also automatically, this will also be X only, right? And so that X value, this is a line of charge here. Now in this we can clearly say that some charge is enclosed here. Some charge is enclosed here. Therefore in the second case we can calculate that charge enclosed is equal to lambda into 2x we can write. Because 2x is the total length inside we are taking here. So therefore it will be equal to lambda into 2 into that x value we can write simply by using this triangle here, Pythagoras theorem. So which we can write it as under root of r square minus d square, right? And therefore this flux passing through that will be equal to 2 lambda into under root of r square minus d square by epsilon naught. So this is the flux passing through that spherical surface. So in the previous recent IIT question is there, I think in 2018 or 17 question, I am not sure. So just they give certain angle here. This angle, total angle is given 120 degrees. So if that 120 degrees is given, from that you can calculate, just we need to calculate this length of this wire here. So length of the wire we need to calculate. And so then from that we can calculate this length of the wire here. For example, if this total angle is 120 degrees is given, so I can divide this 60 degrees and 60 degrees here. So then this will be 30, or you can say this is R means this side will be R sin 30 you can write. Sorry, sin 60 if this angle is 60 degrees. So that means total length will be 2R sin 60 you will get. And then 2R sin 60 into lambda by epsilon naught. That will be the flux passing through that surface there. So like that we can answer such a type of questions there. And in this only, in this example only, now suppose, so write it as the next continuation of this. For example, let us take directly this question. If it is not a line of, charge, for example, it is an infinite non-conducting plane of the charge. So now let us how to write the flux passing through that. Write it as the next problem there. That means this is a line of charge. Now instead of this line of charge, I am placing it in plane of charge. Suppose I am taking this infinite plane of charge is placed like this. Assume it to be passing through the sphere like this, having some surface charge density sigma. So for example, this side I am giving here. This is placed at a distance of r by 2 from the center. So write that problem. An infinite non-conducting plane. An infinite non-conducting plane is passing through an infinite non-conducting plane having surface charge density sigma. Having surface charge density sigma on one side, surface charge density sigma on one side, is passing through an imaginary sphere of radius r, is passing through an imaginary sphere of radius r at a distance r by 2, at a distance r by 2 from the center as shown in figure. Then find flux passing through the imaginary sphere. Then find flux passing through the imaginary sphere. So just the same we need to calculate the Q in. So for that we need to calculate this is a two-dimensional, that means planar surface, we need to calculate the area. And to calculate that area, suppose I am taking this as a radius here. So that side you can write that as, that means this angle is 60 degrees, 30 degrees you will get. Or you can write that just that r is equal to, I can write that as under root of r square minus r square by 4 by Pythagoras theorem. So that means root 3 by 2 r you will get this side. Now it is a plane here. It is a plane in the sense if you are placing that, then inside this sphere you will get a circular disc of radius r. Got it? It is not only, it's a previously only this length we need to calculate because previous one is only line of charge. It is a two-dimensional plane here. Two-dimensional plane means here this part what we are drawing here in three-dimensional, that will be a cone actually you will get. This means this triangular part what I am drawing here, that you will get in the form of a cone. Here this will be the base of the cone here. That means this will be a base of cone of radius small r. Then the charge inside we can write as, charge enclosed we can write as sigma into pi r square we can write here. So this is a charge enclosed here. So sigma into pi into r square is nothing but 3 by 4 into capital R square. Therefore I can write this flux as, this net flux we can write as q inside by epsilon naught. So which we can write as pi r square, that means 3 pi r square into sigma by 4 epsilon naught we can write. So that is a flux passing through the surface. So that is the difference there. The previous one is linear charge density. So we are taking only this length here. This is a two-dimensional plane of charge here. So we need to take that area, that surface sigma into area of this plane inside this cone we need to write. That is nothing but in the form of a base of that cone you will get. So pi r square we can write, where r is given by this expression. So that is a flux calculation here. So we need to identify that we need to calculate the charge enclosed by the given surface whenever such a problems are given. So if you are able to calculate the charge enclosed by the surface, from that you can calculate the flux passing through that. So these are some basic problems based on that. In the next case, in the next class we will discuss some more problems based on these flux calculations there. And after that we will go to the some derivations, and then we start some applications of this Gauss law there. Thank you.